much, Andrea. I'd like to start with a slide that is perhaps our future in exploring Mars. And I hope I see there's some young people in the audience. I hope one of you one day is this astronaut on Mars. I hope it happens in your lifetime. Adjustment, there we go. And doesn't it look like fun exploring Mars with your jetpack and discovering life and driving around in a nice little vehicle and having no fences, a planet to explore, just like pioneers in Washington, what, 150 years ago? Very exciting, and I think this will happen one day. Unfortunately, it's very hard to predict which flag will be on the astronaut's arm. Will it be the American flag, or who knows? Chinese, Indian, maybe some other country. It may not happen for a long time, the way our budgets are going. It certainly doesn't seem like it's happening soon, but this is the future. And if you go back in the past, Mars was nothing like a world at all. It was basically a fantasy. It was a mythology. It was a god. It was a dream. It was the source of stories about aliens and that sort of thing. Very little was known about Mars before the space age. In fact, when I was a student at Berkeley, University of California in Berkeley, thank you, and a long time ago, if you went to the library and looked at Mars, there was a chapter in a book on the planets that was about 30 pages. That was about all that was known: its size, its orbit, some colorings on the surface, it had a polar cap, that sort of thing. And all of our knowledge started 400 years ago with a man named Galileo, who invented a telescope that was good for observing the sky. The telescope at that time, he didn't invent the telescope. He was using it in Italy as a military device so he'd see the ships coming before anybody else, and he was trying to sell it to whoever the commander of the military was at Venice at that time. And so he was making telescopes as military devices, and then he happened to turn it up towards the sky, and that changed everything. And within 6 months of his observations, he had already published a book on astronomy. He knew that if he didn't publish, people would never know that he had ever done it. So he had written a book within 6 months of looking upward. And the telescope continued to be improved until within 70 years later, in 1683, we're actually seeing maps of Mars being drawn. Now, this is a map that could be drawn by a 3-year-old, I understand, but and truthfully, with a map like this, you can actually watch the rotation of the planet going around, and you can measure the length of the day on Mars in 1683, and it was 24 hours. So they thought, well, Mars is very much like the Earth with a 24-hour day. It turns out, a little more accurately, it's actually 24 hours and 40 minutes, but pretty darn good. So very rapidly, things improved, and maps were made, and so forth. And I like to point out an Arizona astronomer who is quite important in the history of Mars, and that's Percival Lowell. And Percival Lowell, observing here on his telescope in Flagstaff, Arizona, on a place called Mars Hill. Today it's known as Lowell Observatory. He spent hours and hours and hours looking through his telescope, and he got a lot of the features right. Here's a Hubble Space Telescope picture, and you can see he really did fairly well. In fact, he did a little too well, because he found a lot of things that actually we don't see anymore today, and all these canals. But based on these canals, he had the idea that there was a race of intelligent beings on Mars who were building canals from the polar region to the equator to offset drought. And therefore, they needed those canals to water their crops. And truthfully, in Arizona, we now have canals from the Colorado River cutting all the way across Arizona to Tucson, which is 300 miles or so. And we were doing the same thing. So it wasn't such a crazy idea, it was just a wrong idea. And because of his books written about intelligent life on Mars, he started literary people thinking about what the beings that lived on Mars might be like. And he really started science fiction, which to me was a wonderful thing. When I was a kid, I love science fiction, and my father would take me to the library every week. I'd get a stack of science fiction books, and I was gone for the whole week, flying around in space in my armchair. So I had all kinds of ideas on Mars. And in the age of 13, this is what I thought Mars was like. I thought, there's Peter Smith with his sword rescuing his girlfriend from the six-legged apes. And this is the way I thought space travel would be and how exciting it would be. And I wanted to make my career in space because look at the fun you could have. Yes, well, that's not the fun you do have, unfortunately. If you do set your career in space, you have to leave your science fiction books behind. And then you find out that compared to Earth, Mars is an extremely dry place. So look at the different color there. And there are some clouds, and they are water ice clouds, with very wispy, thin atmosphere. It's 1.5 times further from the sun, so it's cold. You're not near the sun anymore. So it's cold, it's dry, and it's a very barren, rocky place. But it does have some interesting features. It has 2 moons instead of 1. This is Phobos. Phobos is very close to Mars, and it orbits, and I think in a 4-hour orbit, so it goes around and comes around a couple times a day. And it's a very exciting moon. We have another moon further out called Deimos. These translate to fear and terror. So I'm not sure what the message is on Mars, but it's not the romance we have with the moon on the Earth. It's fear and terror. Now, we have been to the surface of Mars, so I can tell you exactly what it looks like. Even in 1976, we had landed on the surface of Mars, and we knew that it was a rocky, dusty sort of place. And in fact, it looks a lot like the Scablands. And as we were preparing for a mission, I'll show you in a little bit, we actually came to the Scablands and took bus tours around to understand the rock distributions and what a floodplain looks like, because as you'll see, this is a very similar environment to the Martian environment. Now, the Viking landers were there. Carl Sagan was a member of their science team, and he was there particularly to look for life signatures. However, not finding organics was a big setback. Organics are what makes up our bodies, and everything we eat, and all the creatures we know. They're all carbon-based molecules living in a water-rich environment. So when you find a place with no water, no organic molecules, it's hard to think of what kind of lifestyle there might be there. Now, people always say, well, it's a different form of life entirely. I ask you, try and think of what other form of life there might be. It's really a difficult problem to come up with the complexity that we need for life in terms of all the functions that we consider part of our daily lives, and try and think how you do it without any carbon-based molecules. I challenge you. So there was 2 landers thousands of miles apart, and they both saw hyper-dry soil, no organic material. And you might think, well, maybe their instrument didn't work, but they did see some carbon, hydrogen, chlorine molecules. And so they thought these might be cleaning agents that they'd used in their instrument, and therefore the instrument worked just fine. Life experiments actually returned positive results at first, but because of the lack of water and the lack of organics, they were thought to be caused by oxidants in the soil, so chemical reactions instead of biological reactions. So the surface, very dangerous to life, intense UV radiation, cosmic rays come down to the surface. It's a dangerous, dangerous place. So for the last 35 years, these Viking results have taught us that it's probably not going to happen to find life on the surface of Mars. And by the time I get to the end of my talk, we'll see if you still believe that. Now, the NASA strategy for exploring Mars in the last 20 years has been one of trying to determine if life ever arose on Mars, and ever arose, meaning even way in the distant past. It could have died out and not be there today. Understanding the climate, characterizing the geology, and preparing for human exploration. And the common thread across all these themes is liquid water. Liquid water. So the idea on Mars has been to follow the water, look for any water signatures, and try and understand the availability of water on Mars today and in the past. to do that, we've had a lot of missions. And right now, in the present, we have 3 orbiters. One is a European orbiter, which is the Mars Reconnaissance Orbiter, and the Odyssey Orbiter. There's the Phoenix mission, which is no longer functioning. There's 2 rovers. One of them is stuck in the sand dune and is apparently not communicating. So there may only be 1 rover. They haven't officially given up on it yet, but it's not looking good. And even if they do get signals back, it's not clear they'll be able to ever drive it again. So probably we have 1 rover on the surface and 3 orbiters today. And the orbiters could last a long time. In 2009, we were supposed to have a mission, but they were not ready to go, and they pushed it out to 2011. So this Mars Science Lab will launch later this year and get to Mars in 2012, and I'll talk about that. We have an orbiter coming up in 2013 that's going to measure atmospheric properties, and it gets kind of murky out here towards the end of the decade because budgets are having trouble. But we'll see. And the important thing is all of these missions are starting to return data from Mars, and the amount of data is huge. Like I told you, we had a little chapter in a book 50 years ago, but today we are getting such a huge amount of data. It's, gosh, how do you describe a terabyte of data? And really, this is an underestimate. This is an old slide. There are 100 terabytes of Martian image data coming back, to the point where those people that are actively operating this mission have never been able to look at all the pictures that they take with their own camera. And if you think about it, if you put one of these pictures on the wall, it would be about the size of this whole wall, a lot of detail. And in order to look at all the pictures, you have to change those about every 10 seconds for the next 6 months. So how can you look at all that data and understand it? And so if you are ever interested in Mars, this is a time where you can get involved and you can be the first to make discoveries because nobody's actually looked at all the data yet. So there's an opportunity for young people. But we do have a very good topographical map of Mars, and this was done by a laser altimeter orbiting Mars, where you can reflect a laser beam off the surface, measure the time it takes, and you know the speed of light, so you can accurately gauge the height of every feature on Mars to within a few centimeters. And you see great big canyons. This is, impact craters. And this crater is about, 1,000 miles across, and you can see the debris that's piled up around it, huge. Another crater, lots of craters in the south. And if you make a Mercator projection with it, the interesting thing about Mars is the southern part of Mars is kind of in this orange zone. It's high, and it's heavily cratered, and it's heavily cratered means ancient because as craters come in over time, they get erased if you have erosion and a new surface developed. So if you have lots of craters, that's an old surface. If you have no craters, it's a brand new surface. So ancient surface, 4 kilometers or 3 miles higher than the northern plains, which are very smooth and young. So what does that mean? What you think about it? We have 6 successful landers, and the first one I want to talk about is Pathfinder. We're going to talk about Opportunity and about Phoenix. Phoenix being the one that landed in 2008 way north in the Arctic region. So in 1997, I was lucky enough to have built a camera that took this picture from the university, and we landed with a great fanfare on July 4th, 1997, and were able to drive this little rover called Sojourner around the spacecraft. And I was the one taking the pictures of it, and with my team. And we were exploring the rocks and the soil. It looks very much like the Viking landing site. In other words, it's dry, it's dusty, there's volcanic rocks, and it doesn't look like a place where you're going to find much life. I was hoping, of course, to discover life on Mars and be famous for the rest of my life. We basically verified what everybody already knew, so that was not a big step in my career, unfortunately. So the mission lasted about 83 sols. A sol is a Martian day, the 24 hours and 40 minutes. and watched the rover go around. And we saw these beautiful hills in the distance that we called the Twin Peaks. And they're not very high, but they look a lot like a mountain in Tucson called A Mountain, where they put the A of the university on a mountainside, and rocks and painted it white. So there was kind of like a little A up there, and it was kind of nice to see that, and made me feel a little bit. So we used to say that Mars is really like Tucson without the cactus, and in some sense that's true because there's a lot of volcanic material around Tucson. So if you superimpose the rover at different points in its traverse, you can see kind of its pathway around the lander. So there's the Twin Peaks out of the left, and this is a rock we call Yogi Rock because it looked like a bear nose out here. And no, we aren't really bad at driving. We actually were measuring the composition of that rock. This was not a traffic accident. And then we took off in this direction to the right, and you can see at various stages the rover going around the lander until it got stuck on a rock over here. That was a mistake. That was bad driving. Anyway, we lasted for about 85 days, and then we lost communication with the lander. However, the rover is autonomous, and for all I know, it's still going today since it's on solar power. It's nothing necessarily would have killed it. But the message was that modern Mars is very dry and desolate and not very supportive of life. So what about ancient Mars? If we look at some of the ancient features down in the southern hemisphere where we see all those craters, we see old river valleys. And these old river valleys are very much like the scablands in terms of being floodplains. And so they have, water has not come out of snowy mountains, it's come right out of the ground. In fact, there's a volcano over here that might have released heat and released the water, flows downhill and moves out into a plain carrying all kinds of rocks and debris with it. We find all kinds of different features, including another river with a delta in front of it. And this delta, excuse me, is very much like the Mississippi Delta. It'd be like a river flowing into a lake or into a bay, and all the sediments get dropped to the bottom as it does that. Other river valleys where you can actually see the stream bed inside that created the valley. So you can imagine that there was lots and lots of water on early Mars, maybe 3 or 4 billion years ago. Here's a meander and a river, and it's been cut across, so this could have been an old oxbow lake. Lots of beautiful places on Mars that have been photographed from this high-rise telescope in space. All kinds of interesting places that one day we may explore. Color variations are to be found, all kinds of layering. This is some sort of sedimentary features. And because this is near the Columbia Flint basalts, I have a picture of Mars that looks very much like the basalts that you have here in Washington. And these are the columnar basalts that you see in the road cuts all over eastern Washington. We also have sand dunes on Mars, lots of sand. There's no lack of sand. They make beautiful shapes and nice colors. But when we get back to water, you can actually see places where it looks like there's water there today. And the water there today would have come out of the ground, like out of a water table. This is the edge of a crater, and the bottom of the crater is down below. And you can see these stream beds coming down the side of that slope. Originating not at the top, but somewhere at a layer a few hundred meters down below the edge. So water flowing under the surface of Mars. And if there's water under the surface of Mars, is that a habitat where life could have evolved down under the surface and found a place protected from the hazards of Mars and a place where life could live on even today? We also see ice features. This is a glacier that's been covered in dust and rocks, so it doesn't look like a glacier. It's not white. but the ice could be just a few inches below the surface, maybe a foot below the surface, and you can see the flow patterns as it comes over a ridge from a high plateau down to a lower valley surface. Ancient lake beds, we saw layers today. We went out on a little excursion not far from here, and we can see many, many layers caused by some of the flood action during the glacial period. And very similar features on Mars, where you have hundreds and hundreds of layers of sediments inside of a crater where water has come in and dumped its sediments, drained out, come in another season, dumped its sediments, come in another season. So periodic flow of water and thick lake beds. One of the more interesting things that we found recently is that there's a source of methane gas under the surface on Mars. Now, methane gas is what's called swamp gas on the Earth, and swamp gas is caused by the decomposition of organic material on the Earth. So is this a location where out of fissures and cracks in the ground we're getting decay products or respiration products of some sort of life form? Or is it a geologic process that would require active volcanism and underground water? So either way, it's an interesting discovery, and will be followed up at one of the next orbiters later in the decade, assuming they actually fly. Okay, so ancient Mars appears to have a lot of interesting water features. Modern Mars has a few. Maybe there's a little water left. It also has a little bit of methane. And it's in this light that we've sent a rover called Opportunity to Mars. And this rover is able to drive for almost 20 kilometers, 15 miles over the last 7 years. It's been alive for 7 years and has done some amazing things. And the Opportunity rover landed in a place in the middle of Mars, right here, right on the equator, not far from the huge canyon feature called Valles Marineris, a little bit off to the side. You can see the old river systems going up to the lower plains. Here's another riverbed. Huge volcanoes. Volcanoes on Mars are 3 times the height of Everest. They can be as much as 27,000, no more than that, but 20 kilometers high. It's like 15 miles high. They're huge. And the base of this volcano here is the size of Arizona. So you imagine a volcano the size of Arizona with a peak 3 times the height of Everest. A very interesting feature with a big caldera on the top. 3 other volcanoes lined up here and another one there. That's a very volcanic active area. They may still be active, but they're dormant at the moment. Now, an orbiter has measured the composition of this part of Mars right here and found it to be very different than any other part of Mars. And they mapped out the composition of a material called hematite, which is an iron oxide that forms through the action of liquid water on iron. It's kind of a rust product. Hematite is formed in wet environments with iron. And so the plan was to land right where this red dot is, inside this hematite area, and hopefully this is a place where water has been important in the past and maybe even in the present. And the rover was tasked with finding that evidence of water. So when you send a mission to Mars, you launch from the Earth when Mars is in alignment with the Earth. And you can only do that every 26 months because the planets move at different speeds. It takes 26 months for them to realign. Then you can launch, and then you shoot towards a place in space where Mars and spacecraft meet. That takes about 8 or 9 months, maybe 10 months. And then when you get there, you come screaming in at a very high velocity. And in this case, when they landed using airbags, so they were bouncing. And they bounced along the surface, and they rolled and rolled, and they ended up actually in a crater. It was called Interplanetary Hole-in-One at the time. Because this is inside of a crater, and there's the edge of a little crater. It's not a big crater, maybe the size of this room, and the height is maybe 3 or 4 feet high. But believe it or not, what they were looking for is sedimentary rocks. Those are the rocks that are not volcanic rocks, but are caused by sediments or some sort of water-rich process. And the first picture they took was this picture right here. And they, wow, what are those rocks? They don't look volcanic at all. And I want to point out a couple things here. One, they landed to find hematite, and they have an instrument I'll show you in a second that can see hematite. But if you look down here, that's not very visible, but if you look down here, there's some little blobby marks in the surface. Those are marks the airbags made as the lander bounced into the crater. You can actually see them on the surface because it pressed the soil down. It's kind of a heavy lander, so it put a lot of force down there. And so you see those marks. And now the next picture shows you the infrared instrument that shows where the hematite is and where it isn't. The hematite is the red material, and this is also considered red. But look where the airbag marks are. How can you possibly land an airbag on a surface and destroy the signature of hematite? How would that be possible? This was just astounding, you know. I mean, if it's hematite, it's hematite. I mean, you don't just put it and it turns into something else. How is that possible? And what are these rocks? Those are not the hematite that you might think they would be. It is something else. So right away we were stuck with these mysteries of what the heck that could be. The next slide won't show you, but the future slide will. We ended up, here's another picture. There's our airbag lander. We drove off of it with the rover and came out of the crater. So this is looking back at the crater. And we came over to another crater, and that's where we're going to be able to answer this mystery. This is the other crater we went to, Victoria Crater, quite a large crater, half a mile in diameter. And there's the actual Opportunity lander right here on the edge. Here's a blow-up of it. You can see its shadow right there. You can see kind of a fuzzy thing in the shadow. And if you look here, that's the shadow of the camera. That's how accurate this orbiter camera is. You can actually see the shadow of the camera of the lander on the surface. So we got there, went down into the crater. We could see layering in the crater, just like you see here in eastern Washington. Cross-bed dune-like features that are very representative of water-rich environments with all kinds of little layering caused by water flowing on the surface. Like the shallow sea, you see wave-like features and all kinds of things. And the third layer up here that is definitely a very water-rich environment. Now we could dig into these rocks and we found out they were sulfates. These are, I think, calcium sulfate. It's called jarosite. And we could dig into them with a little tool and measure their composition. But the hematite is not in the rocks. It is in these little bluish things up here that you see on the surface. Let me see if I can get you a picture. These little things are hematite, and they were called blueberries because they look the size and color of blueberries. See these little knobs and these little pea-like things? In the layers, they're actually eroding out of the rock. Eroding out of the rock, and they have a stronger composition than the rock, so they don't erode away. When the rock erodes away, these little blueberry shapes are left behind all over the surface. And when the airbags landed, they pushed the blueberries down into the soil. And so when you could see them on the surface, it was fine. When you pushed the airbag down, they got pushed into the lower soil and they disappeared. So that's why you can see the airbag marks. Very strange. Nobody predicted blueberries on the surface. And they cover an area the size of Oklahoma. It's not just a small group. It is littered over an area the size of Oklahoma. So our understanding from the Opportunity rover is this was a very rich environment in the past, and there was a lot of iron oxide in the water that came through the rocks. The rocks would be sulfate rocks. The water would be super iron rich, very acidic. So in this kind of acidic environment, like in Rio Tinto in Spain, this is an actual river in Spain, That's the kind of environment you would have had in the past. I don't know exactly when, but certainly billions of years ago. And is this the kind of environment you can find an origin for life in a very acid-rich, iron-rich environment? Well, who knows, but it just doesn't seem very likely. So people are a little disturbed by the acidity of this environment. They wonder if life could ever evolve in this kind of environment. Definitely it's wet. Okay, with that in mind, I proposed the Phoenix mission to fly in 2007, which landed in 2008. And it was based on a whole different model, not looking at ancient Mars, not looking inside of rocks and trying to understand their history, but looking at modern Mars in the polar region. And in the polar region, we've always known that there's an ice cap. This is the North Pole, that's a water ice cap. But always in the past, until 2002, we could see nothing around it except dry, rocky soil, just like we see in our landers. Until there was an instrument on the Odyssey spacecraft that could measure neutrons and gamma rays that were emitted when cosmic rays excited the surface and were very sensitive to underground ice. So here's a map of underground ice that is not visible on the surface, and you can see there's high concentrations at places far away from the polar cap itself. So the Phoenix mission was targeted at a spot right about there, and our goal was to try and understand what the properties of those ice layers were, how close to the surface they were. Is it an environment where perhaps life could have existed now or in the past? Well, the dangers of landing on Mars are extreme, and I want to show you an animation of what it's like to land on Mars and what it was like for our Phoenix mission. Okay, so we come in at 15,000 kilometers an hour, 12,000 miles an hour. We release our package that got us safely to Mars, our cruise stage, and we enter at this high speed, and we remove all that huge energy of entry into the upper atmosphere through the friction of interacting with it, until we get about 1,000 miles an hour, and then we can release our parachute. Now, as we get close to the surface, about a kilometer from the surface, we're going to drop our heat shield, and we're going to extend our legs, and after taking a picture, we get the most dangerous part of the whole mission. So right after this dangerous part of the whole mission, right now, we just drop and stop ourselves with 12 thrusters and slowly work our way to the ground. We hit at about walking speed, 3 or 4 miles an hour. So that's a very gutsy landing, and that's what scared everybody half to death, and that's what made our landing so exciting. And then, of course, we had to have solar panels, or else we have no energy. So those had to work. Here's our camera we built at the university. And we have a weather station that's going to come up in a second. And in here, in this package, is our robotic arm. It's protected so that we don't bring microbes to Mars and plant them in the soil. That's a sterilized arm. And our mission is to dig beneath the surface, to pick up samples, to analyze them with instruments on our deck, and to try and understand something about the Arctic region of Mars for the first time. So what it shows next is picking up a sample. It has a little scoop. There's a camera up here for watching the action. Well, it happens very slowly, but for us it's action. So you're operating this thing from 200 million miles away, seeing only through the eyes of the camera, feeling the surface only through the arm, understanding the nature of the soils only through the taste buds that you have inside of your instruments and your sense of smell. Another instrument here that I'll show you in a minute. And then we can look at the clouds where the LiDAR beam, the laser beam shines up and actually reflects off the clouds, and we can learn about clouds. Now, one of the amazing things to me during this landing was the fact that we could actually attempt to take a picture of it from an orbiter flying by. The orbiter was our communication path link. So we would communicate to the orbiter, which would send the signals down to the Earth. And during the parachute phase, we tried to take a picture. And we didn't know we were going to land to within, I don't know, 30, 40 kilometers. There's a lot of uncertainties in this business. So we had an area picked out that was very safe. And we took a picture. Here's the picture in this little box, blown up, is the parachute and the lander, taken from 200 million miles away with one spacecraft looking at another at just the right time and just the right direction. And while it looks like it's landing in the crater, it's actually not in the crater at all. It's a few miles in front of the crater. It's a long slant path looking sideways at it. After that picture, we took another picture when it was landed, and here's our spacecraft on the surface of Mars. You can see the deck, the blue central thing. You can see the two solar panels on either side. You can actually see this area where the thrusters have scoured away some of the dust on the surface. Also notice that the ground is not flat, it's patterned, it's kind of rippled. And that's caused by the expansion and contraction of the underlying ice. That's the kind of patterns we wanted to see. So the spacecraft in this drawing shows where the instruments are. We have weather and climate, and we measured day by day what the weather was like on Mars and studied the clouds and dust. With the camera in the arm, we could dig and look around with the camera in the arm. And then gathering samples, we could analyze them on the deck in 3 instruments that we brought with us. Well, the first thing we did on landing was to check to make sure that the 3 lander legs were secure and weren't tipping on a rock or something. So the first thing we did was look under the lander. We could see these 2 feet. But the one in the back you couldn't see. So the next picture shows looking under the lander for the first time. And there, under the lander, its foot is very secure. But it was amazing to see that the ice table we were looking for is exposed by the thrusters. We didn't have to dig at all. Unfortunately, the arm, which is, you see the edge of it here, can't reach there. So we're hoping that wasn't the only ice you could find on Mars. Here's the thrusters up here, and you can see they've cleared off a very nice little surface for us to investigate. We just can't reach it. I hope the next picture shows up. It's kind of dark, but the next picture shows this strut right here. So not only did we clear off a nice landing area, a nice ice area when we landed, but we splashed things up on that strut. And this strut shows little blobs on it. This is the 8th sol of the mission. This is the 44th. And if you look at some of these blobs, they have actually coalesced. Are these liquid droplets? They look like liquid. They're not icicles, are they? You guys know what icicles are like. I don't. I mean, they don't usually grow from the top of. They don't grow from the top of something. They come down from the bottom. And so I think these are very strange little blobs that over the 44 days here actually get bigger. Look at this one; it's growing. That one, this one, these 2. Very strange. So this caused basically a civil war within our science team. Those who said, well, that has to be ice, and others who said, those are liquid. And we had a paper published saying they were liquid, and people said they were ice, never actually got around to writing a paper. So I think I could say with some certainty that these are liquid droplets. And the only way you get liquid on Mars is if it's a brine. You have to put a lot of salt into it. So somehow, in these thrusters hitting the surface and spraying up those ice particles that are probably melted, they picked up enough salt so that they could stay liquid even at the very cold temperatures of Mars, which is like minus 50 centigrade, well below freezing. And I'll try and point out how that might happen later in the talk. Now, this was described to me as one of the most boring panoramas ever taken by Burt Tan, who designs spacecraft, and I was really pissed off when he said that. Actually, I can't disagree too much. You know, we picked the flattest place on Mars with no rocks, no surface features, because we wanted a safe landing. And so we have a safe landing, but now we have nothing to look at. And so our whole mission is about digging into the soil nearby, and you can see some various trenches out here. If you blow it up, fortunately one of our trenches, this one here, does show some white material. But this is a high resolution picture. It's kind of squashed down here. And you can look around out at the distance, and if you're lucky, you might see some evidence of life, like that little white dot. So this is our little polar bear. Unfortunately, there are no polar bears on Mars. And polar bears might wish they were on Mars, the way things are going in the Arctic, but they have no way to get there. And in our trench, this ice was scraped up, and you can see 3 little white blobs right here that disappear over a few days. So what evaporates in a few days? Well, it's got to be water ice. And eventually we got some of this material into one of our instruments and could prove it was water ice. And this is an example of the scoop of material being carried over to our instruments. The camera can look down into the scoop. This is what Martian soil looks like. And it's a little like the soil we saw today out in the field around here. It's clumpy, it makes clods. And you can see these dirt clods that get dug up, and in fact, everything seems to be clotted up there. And this made it very difficult for our instruments, which had little screens to keep the clods out. If it's all clods, it kept everything out. We didn't get samples into our instrument. Of course, we were trying to shake the screens, but we weren't expecting something quite the composition of flour. So when you sift flour, you do it this way, right? Well, we were doing it this way. And it's more like a magic finger bit, it's not really helping at all. And we had a great difficulty getting our samples in. But we were able to get some microscopic pictures. This is Martian soil at 1 millimeter across here. So this is about 10 micron resolution. These are tiny little particles, 50 micron particles. You could feel them in your fingers like grit. And these other particles are as small as flour. You wouldn't, like face powder, you wouldn't really feel the particles anymore. So 2 different types of soil, the reddish face powder type, and these black little grainy sandy-like pieces. Here's another group of them. You see there's red ones and white ones and clear ones and various colors. Don't ask me what rocks they are, because I don't know. They are all rounded and football shaped. You see that? They have been blown by the wind, and the wind will knock the corners off as they bounce along. So this is a soil that's been weathered by wind. And it's magnetic. Those are magnets there. The reason it's all in one clump is because there's a strong magnet underneath. Okay, we have a wet chemistry experiment, and here it is right here. There's 4 of them in a row. And we put a sample in, we add water we took from Earth, we stir it up. Whatever goes into solution, we can measure with instruments inside of the beaker. And the big surprise for us was finding that more than 0.5% of the soil on Mars is perchlorate. I know very few people know what perchlorate is. I didn't know what perchlorate is either, so I'm going to tell you in a minute. But this is a very interesting finding, as you'll see. The other thing we learned is that the pH, the acidity of the solution coming out of the soil is not acidic like it was for the Opportunity rover. Not acidic at all. In fact, it's the same pH as ocean water, just around 8, just a little bit alkaline. So pH of ocean water. This is not an unusual soil that you might find on the Earth. This is kind of a friendly soil, except for that perchlorate. Also, in this picture, you can see a DVD with some little pictures of books. And this is a library of all my favorite science fiction books. That's a free lending library for anybody on Mars who wants to take it home. So, I wonder, who's going to get this DVD? Is it the next 100 years, the next 1,000, the next 20,000, 100,000 years? This thing will be there. It's not going anywhere. This may be the only record that remains in 100,000 years of the 20th century on the Earth. Science fiction. when I realized that after it had launched, I thought, well, maybe I should have added a few other books in there. You know? This can't be the end-all and be-all of our 20th century. Okay, so I promised to tell you what is perchlorate, because I know most people, as I certainly didn't know. At high concentrations, perchlorate lowers the freezing point of water to -70°C, which is below the average temperature of Mars. So where those blobs on the landing legs high in concentration in perchlorate and therefore liquid brines, well, it's not unlikely. They could have been concentrated and splashed up there. Of course, it started at 1%, so it would have had to mix very rapidly under the conditions left by the thrusters under the lander. They're an important energy source for microbes on the Earth. We don't find perchlorate many places on the Earth. It's found in the very driest regions like the Atacama Desert in Chile where it never rains. The reason we have to go to Chile where it never rains to find perchlorate is that it's so soluble in water that if it does rain, it takes all of the perchlorate into solution and carries it down into the water table and eventually out to the ocean. So we don't find it in many places except the driest places. And of course, Mars being exceptionally dry, it's likely you find it there. When it gets into our drinking water, it's a poison at 25 parts per billion, and the way we get rid of it is bioremediation. We use microbes to go down and eat it. So it's a food source. Unfortunately, and the reason we get rid of it in our drinking water is it's toxic to humans. It competes with iodine in the thyroid and causes all kinds of troubles for humans who ingest perchlorate. And that's at 25 parts per billion. Now, if you have it at 1%, which is a lot more than 25 parts per billion, we don't know what the dangers are because nobody's ever taken that much. And you would have to protect yourself against these poisons if you were a Martian astronaut. So it's a new thing to know about. And of course, there may be other things in the soil we still don't know about. So I wouldn't send anybody to Mars until we understand the toxins in the soil. But the good news is, it's the oxidizer in the solid rocket fuel that was in the solid rockets that actually launched us off the Earth. That's ammonium perchlorate. And you need an oxidizer because as you launch up into the atmosphere, you get above the oxygen layers very quickly, and you still need oxygen to burn your fuel. So you carry it with you in a solid form. It's released at high temperature. The same instrument that found the water around the pole also mapped chlorine. Just chlorine, they didn't map the chlorate, they just mapped chlorine itself. And this is the distribution of chlorine. These are the two Viking landers. And if you notice from the color scale, they are at about 0.5% chlorine themselves. And here we are up here in Phoenix, a little off the chart, but if you kind of roll this around, we kind of agree with the 0.5% chlorine. So it's not unlikely that there's perchlorate at the two Viking sites. And what would that mean for that instrument that measured the fact that there's no organics on Mars? If you put perchlorate, a powerful oxidizer, in your oven that's going to heat up the soil and release organic molecules, what might happen? So this experiment has been done with desert soil with a small amount of organics, apart from unit, and the perchlorate at the level that we see on Mars, heated up to 500, just like Viking did. And what do you get? Well, you get what they saw. You get water and CO2. You don't see any organic molecules per se, but you see the carbon, hydrogen, chlorine compounds. This was done by a scientist in Mexico City. And let me remind you what Viking saw. Carbon, hydrogen, chlorine molecules that they interpreted as cleaning agents. I say they're not cleaning agents at all, that they had perchlorate in their ovens. They destroyed the organics that they were trying to measure. And for 35 years, we have had the wrong paradigm on Mars. There's actually organics all over the surface of Mars at parts per million. It changes the whole way we think about Mars. So, they're incorrect. But they can't prove it. However, the good news is the next mission can. The next mission is this huge, nice rover. And the prediction is, and I'll make the prediction here tonight, it's going to measure organics in parts per 10 parts per million. And how are they going to do it? They have ovens just like Viking and just like Phoenix did. And they will see no organics in the carbon, hydrogen, chlorine compounds. However, they have another way of releasing organics from the soil, doing it chemically. The vapors will come off. There will be no high temperatures. There will be no release of oxygen from the perchlorate. And they will be able to see organics in that experiment, not in the other. And that will be proof. Phoenix found it first. So this big rover, let me show you the size of this rover. Compared to our little Sojourner rover and Pathfinder, our Mars exploration rovers, Opportunity, and this is the Curiosity rover that just dwarfs all the others. It's huge. It's like a giant. You notice solar panels. What is this thing? That is a nuclear power generator. This thing is really awesome. I wish I had it. The price of gas these days, wouldn't you want nuclear power to drive you around? Here's the team that's putting it together, Intelligent Curiosity. Look at the size of this baby. It just dwarfs everybody. It's really a very amazing mission. They are not using airbags. They're using a sky crane. It comes down and hovers above the surface, and the rover drops down on a little cord, and they cut the cord, and off it goes, and this thing flies away. So don't forget to watch the landing of Curiosity when it gets there. Not this summer, but next summer, 2012. It has some amazing abilities. They can measure rocks from a distance using a powerful laser. Vaporizes some rock and then looks at the vapor through their spectrometers and can tell you what the rock's made of. Great stuff. Wish you had one of those, Andrew. So, I don't know if the MSL or Curiosity will find life on Mars. I think they'll find organic material, but finding life is more difficult. I think we really are going to have to wait until we get somebody down there. I think without human intelligence on the surface, we're not going to find this material right here. And that pay dirt, it's not so easily found, I think. Maybe we need to drill under the surface, whatever. But humans, I think, are necessary. Not happening soon, but it'll happen one day. And I have another prediction. I'm full of predictions tonight. I think when this material is gathered and brought back to Earth, put into our laboratories where we have the most incredible instruments you've ever heard of, and certainly 30 or 40 years are going to be much better than today. And we can get down to the tiniest grains and blow them up to a size where we can see what the tiniest material looks like. I think I know what we're going to see. We are going to see six-legged apes at the micron scale. And Edgar Rice Burroughs was right. He just didn't get the scale right. So thank you very much.